Now the question I'm going to pose is this. Here's your electric field, the same electric field, 175 kilonewtons per coulomb times I, and 67,500 kilonewtons per coulomb, 67.5 kilonewtons. Being a little inconsistent there. 67.5 kilonewtons per coulomb times J, and you'll of course understand how we go from newtons per coulomb to kilonewtons per coulomb. I just wrote to kilonewtons because I didn't want to write all the zeros. So here's your electric field. Okay. Now let's say that you have a charge Q equals, let's say, 0.003 coulombs at this point, and you want to move that charge this far through a displacement delta S, 0.2 meters times I minus 0.1 meters times J. We want to find delta W, assuming that E stays pretty much constant. Now remember where this came from. We are assuming a 0.004 coulomb charge over here at negative 3 meters, 2 meters. We're moving only a little over 0.2 of a meter, so that the distance from the charge isn't going to change by much, and the direction of the force isn't going to change by much. There will be a change, and we would ordinarily have to do an integration to find the exact result. But for right now, let's not complicate things that way. Let's just assume that E stays pretty much constant and calculate the work done as we move this charge from here to here. Okay, the first thing you should understand is that the work done is equal to the dot product of the force with the displacement vector. So if you haven't done that, you should pause and see if you can write down what that would be. And going to go on. If you calculate the force, I believe you're going to get 525 newtons times I plus 203 newtons times J. And we dot that with the displacement vector. So figure out the dot product. I'll write that down off camera and come right back, and you calculate it yourself. Okay, calculation's fairly straightforward. I believe 0.2 times 525 is 105. 0.1 times 203 is 20.3, which I just round to 20 with some respect for significant figures, and also the fact that the electric field really is changing here by more than would justify keeping that 0.3. And when I subtract that, I get 85 joules. So I believe there are 85 joules of work done as we move from here to here. Now, what is it that's doing the work? Is this work done on the charge? Is this work done by the charge? Give that a little thought, and we'll talk about that in a minute. Well, Q and E give you a force. We multiply Q by E and we get a force. Now, what exerts that force? Well, the field exerts that force. On what? On the charge. So, work delta W that we calculated here is the work done on the charge by the field. Okay, so going to make a statement here. I'm not going to prove this, although it's fairly easy to prove it to people who've had multivariable calculus. It's very easy to verify that this field is conservative. But we'll just say field is conservative. So work done by the field on the charge is equal and opposite to the change in the potential energy. Okay? So that the field is sort of analogous to a gravitational field. Now, it's not acting in the direction you're used to a gravitational field acting in, but this charge down here has produced an electric field up here that acts not like a gravitational charge on masses, but on charges. Okay? It's an electric field that acts on charges and gives you potential energy changes. So that between here and here, the field actually does positive work on the charge, resulting in a change, a negative change in the potential energy of the charge. Our displacement here has a component in the direction of motion. And of course, if you go back to the meaning and definition of dot product, you see how this works out. But right here is our parallel component of the displacement, component of our displacement parallel to the field. And our displacement is in the same direction as the field, and that's why we have positive work, negative change in potential energy. By analogy, you can think of the fact that if we lift an object, we increase its gravitational potential energy. Gravity is down, our displacement is up, so that we're increasing gravitational potential energy when gravity does negative work on the mass. Okay? If we lower an object, its gravitational potential energy increases. If we release the object here, allow it to fall to here, that potential energy goes over to kinetic energy. Similarly, if we release the charge from here, well, we're not releasing the charge. We're actually moving the charge in a direction that it wouldn't go if it was released. So by analogy, if we take a mass here and lower it while moving it along some direction, then the component of the motion of that object in the direction of gravity is what determines the work done by gravity on the object. And the analogy is the same here. Here we're moving the object, and a component of that goes in the same direction as the electric field, so we're losing potential energy just as we would if we lowered an object along a path like this, not parallel to gravity, but with a component in the same direction as gravity. Now, it follows that in moving from A to B, with the field doing 85 joules of work on the charge, what's the potential energy change? You want to jot that down. What's the potential energy change in terms of what we've just said? And then we ask, what's the potential energy change per unit of charge? Remember, we moved 0.003 coulombs of charge from this point to this point. What's the change in potential energy per unit of charge? See if you can answer those questions before I step out of the way and point to the answer that I've already written here. Okay, well, here it is. Change in potential energy, from what we just said, is equal and opposite to the work done by the field. So that's negative 85 joules. Change in potential energy per unit of charge, well, what are we going to do? Well, now that you know it's negative 85 joules of potential energy change, see if you can do that if you haven't already. So you should have paused and done it. But we just divide the potential energy change by the amount of charge, and we get the potential energy change, number of joules per unit of charge, number of joules then per coulomb. And we get something on the order, this would actually come out negative 28,333.3 repeating, but remember there are approximations involved here, so I'm just going to use 28,000. Now, a joule per coulomb in this context is what we call a volt. So you've talked about volts, you've probably dealt with volts, but do you really know what a volt is? Well, now you do. Last comment, we would normally integrate from this point to this point and take account of the changing electric field. We do a line integral. But we're not going to do line integrals in this course. That's beyond the scope of this course, which only requires 1 year of calculus. We'll allude to it because most of the people taking this course in the program we're in right now have had a year or a semester of multivariable calculus and know very well how to do line integrals. But I'm just going to allude to it and put that together as you will. It'll be to your advantage in the future.